Yeah, there you go. You can begin. Thank you.
Okay, the today's session is going to be about understanding the obstetric ultrasound data as well as about pre-processing the data to make it ready for AI model training. So the things that we're going to cover today include the obstetric ultrasound data, how it's acquired, and the forms of obstetric ultrasound data, including standard scans that are taken by the experts, as well as the blind sweeps that we're currently working on. And we'll also introduce how AI has been used in obstetric ultrasound, and then we'll shift the focus to pre-processing parts, and I'll also show you a short notebook that I created and that is more hands-on about code and pre-processing. So let's begin. Let's begin with what obstetric ultrasound data means. From obstetric ultrasound word itself, the obstetric means related to pregnancy, and the thing that you care in pregnancy is both related to maternal as well as the child's health. So the ultrasound really facilitates the care for both child and mother by outputting uh, ultrasound images. You can see in the image how ultrasound works. Basically, a sonographer or a radiologist points a transducer probe. The probe generates sound waves, which has very high frequency, so called ultrasound, and the sound waves move through the tissues of the child as well as uh, the mother, and the waves that are reflected from the surfaces of the tissues are actually captured in the imaging. So the image captures both the anatomy of mother as well as the views related to the child. So the ultrasound is taken by through the knowledge of the experts as well. Mm, yeah, and the ultrasound also provides real-time imaging. So that's a short introduction on obstetric ultrasound data. And here we can see what are the things that the experts care about for the child in when they perform a regular scan. They often look at the placenta location. The placenta simply means a body mass that allows the child that is being developed to get the nutrients as well as oxygen. uh, and Another thing that is important is the fetal presentation. Fetal presentation means how the uh, child is oriented in the the uterus of the mother. So a natural position, the most natural position for the child to be in is called cephalic position. It means that the head is down, so it's a bit easier when the baby comes out. So, like finding out the fetal presentation allows you to see, allows you to plan for the delivery. And another important thing is the placenta previa. Sometimes the placenta that I mentioned earlier grows near the maternal cervix, from which the baby normally comes out. So when the placenta grows near the cervix, then it really creates a complication. It may lead to bleeding. So finding out about the placenta earlier is very vital. So like obstetric ultrasound is taken to find these sort of things before things get complicated during the delivery. uh, Another things that radiologists often monitor is the growth of the fetus along with the age. So sometimes there are like conditions such as growth restrictions, so you can actually monitor these kinds of things. And the cases of multiple pregnancy can also be identified early, so that uh, some of the anomalies that can be associated with multiple pregnancy can be identified very early. And another thing they also look at is the volume of the amniotic fluid. That's the fluid that exists in the uterus, where alongside the baby, and it helps to regulate the temperature of the baby. Also allows the breathing space for the baby. And so like with and this all and the volume of the amniotic fluid, the monitoring of the volume of amniotic fluid is essential, because in the case of less volume or the more volume than necessary, both can lead to complications. So these are really about the things that the radiologists care about when they take ultrasound to monitor both the child and the mother. And the ultrasound images are mostly like the grayscale images, and the images that they capture are like they can be in still images, like the standard views of the fetus, as well as a full video. And the file formats that the current devices like export are DICOMs, as well as the more familiar PNG, JPG, and MP4 formats. We'll later see in the notebook how we can work with DICOM images. Uh, these are some of the still images that radiologists often capture. Like the first one is the head of the child, and the second one is the abdomen, and the third one is like the femur. These, like the radiologists often monitor these kinds of anatomy of the fetus to like monitor the everything that I explained earlier on the amniotic fluid, as well as like the growth restrictions or the gestational age, finding gestational age. They monitor these kinds of anatomy to find those metrics. Let's now look at why ultrasound. Ultrasound is preferable in obstetric setting because there are many portable devices now, so it makes it easy, and it is also of lower cost compared to other mechanisms such as MRI. It provides high temporal resolution, and unlike X-rays that generate radiations which are harmful for both baby and mother, it is radiation free. So ultrasound is like preferred in these situations. There are also some challenges associated with ultrasound, such as the field of view is a bit limited because you capture ultrasound in a plane, and it is operator dependent. Like you need experts to find the right set of views. uh, yeah, and the quality of image, as well as the images, the semantic content of the images depend on who take it. So like these are the challenges that exist with ultrasound. I want to introduce like two types of data that are uh, currently taken with ultrasound, with obstetric ultrasound. The first one is the images that I like, similar to the images that I previously showed you. This includes like the standard view of the fetus, like shown in the left one, or the like ultrasound data in the form of blind sweep videos. Uh, you can see the video playing on the right side of the screen. So this was actually taken by experts, but without looking at the ultrasound skin. I'll later introduce you to blind sweep videos as well. Uh, Now, like the standard acquisition protocol for ultrasound is that the expert takes the probe and like finds the relevant anatomy of the fetus. For example, in the first image, you can see that when you're interested to find fetal abdomen, you have to like move the probe, and with your domain knowledge, you can find the right sort of plane that is that captures the abdomen. And if you're interested to look into the standard view of brain, then you have to find the view associated with the fetus head. And if you want to find maternal cervix, so the maternal cervix is uh, essential to find the case of placenta previa that I showed you earlier. Placenta previa, like if it develops uh, near the region of maternal cervix, then it can lead to bleeding and other complications. So you might have to find the views to see whether the placenta is growing over there or not. So basically what I'm trying to say here is like you need experts to find all these kinds of right views to see the right diagnosis. With this is with the standard acquisition that the radiologists do to find out or monitor the health of the child, as well as monitor the status or find anomalies related to fetal health. Like with this imaging, you can see that a child is a child can have like multiple different areas for multiple standard views. The left diagram shows like the standard views that exists over the entire like fetus body, and you can see on the right diagram that that the the expert have to move the probe in like sort of with the knowledge of with domain knowledge to find the right views, and it's a bit complicated. So like finding with the standard planes you can diagnose anomalies as well as estimate gestational age or other parameters, but it's dependent on experts. Uh, and I want to introduce blind sweep to you in this context. Like blind sweeps really mean that you don't have to rely on experts to find the right sort of views and use the domain knowledge. You can just like take the scan in a fixed trajectory over the entire uterus. So you can see on the right the picture. It shows that in the first step you could just take a sweep from bottom to the up, and in the second step you could just shift the probe a bit on the left side so it captures a different anatomy of the fetus. So with this sort of protocols you could like capture the entire uterus of the mother, as well as it could capture the entire fetus anatomy, so you wouldn't require the help from the experts to find those sort of views. So like this is more this captures the anatomical views that I showed you earlier in this slide in more passive way rather than actively looking into it. And yeah, it's more protocol driven. So like you don't select the plane, you don't move the probe and select the right plane, you just capture everything. This was an example of a blind sweep data. You can see that the child is like present in the transverse position. His head is on the left, while the buttocks is on the right in the image. So if you take the blind sweep from right to left, then you would expect the the anatomy to like first see the abdomen and then eventually see the head, because the head would be captured later on. So if you take the sweep in this way, you could like also capture head as well as abdomen, but you wouldn't like move the probe in an expert way. You would just capture everything else along the way as well. So uh, this is a blind sweep data. And like just to reinforce again, with standard scan you use expert knowledge to find the right views and measure, estimate, and find anomalies from the right views. With simplified protocols you like take linear sweeps, capture everything along the way, and you could assess those the anomalies as well as measure using AI, or you could also like you also give ex- you could also take the opinions from the experts to find the anomalies. Blind sweep data is really needed because firstly the commercial devices that are in the hospitals are a bit costly, and shifting to blind sweep protocols allows you to use handheld ultrasound devices. And secondly, the the challenge with the standard scan is you need experts, and like in the rural areas or the settings uh, in LMIC, low and middle income countries, you often do not have like expensive devices as well as experts in rural areas. So you could teach the blind sweep protocols to even like non-professionals easily, and you could like like find anomalies or do fetal assessment from blind sweep data over the teleradiology setup, or as well as with using AIs. So, and this shows like the prediction of gestational age using blind sweeps rather than the standard views, and it shows that like the prediction from blind sweeps actually outperforms those taken by experts biometry, as well as from the last menstrual period taken from the patients themselves. So like really do have a potential with the blind sweeps, and actually for the final hackathon as well, you will be using blind sweep data. So I think putting these things into context will help you uh, for the final hackathon as well. Uh, this shows like some of the differences between standard scan and blind sweep data. Everything like I've already mentioned to you before. Uh, do you have any questions regarding these?
Oh, but I can read for you one of the comments.
Okay.
Yes, there was a comment that somebody said they love the blind sweep model. It would make life really easy. And yes, I agree. Considering that's what you're doing, it does make life easy. We get nurses who are able to do the sweeps, non-expert midwives. There's a question by Abdisa who's asking what does a blind sweep mean? So just um, explain whether it's a new model. The blind sweep is one question. And then I guess the other question, will the AI read the video in the blind sweeps or the images? Maybe that's another one. And are there any number of sweeps to be taken within the blind sweep? So maybe you can answer those three and then we'll do the others once you continue during the next question session.
Regarding the number of sweeps, like it's not like everything is not tested with the number of sweeps currently with the current models. Uh, One of the standard things that they do is use six sweep protocol. Like it's the three vertical sweeps and three horizontal sweeps, assuming that it would be enough to capture everything that is relevant. But like there are also limitations with this protocol. Like sometimes the maternal cervix doesn't show up way down, and like sometimes like you don't even need six sweeps, because like during earlier stages of pregnancy, like the first trimester or the second trimester, the uterus is a bit small, and even like few sweeps can be uh, useful is enough, and sometimes the rest of the sweep doesn't capture anything. People have like tried with more other protocols as well. Like we have been trying with nine sweep protocol as well as like eight sweep protocol. So it's not like definitive at current stage, but like yeah, I think that answers the number of sweeps question. And another was on what is the blind sweep data. Like basically with the blind sweep, the operator or the one who take the sweep do not look at the screen while taking the data. So that is why it is called blind. It is made that way so that the operator doesn't like get biased to find the right views or like better imaging quality. So the the blind really means that you don't look at the screen, you just have a protocol that is already defined, and you just follow the protocol to take the sweeps. Does that clear up?
Yes, it gave I am seeing a thumbs up from both people who asked questions and from others. I'll take some of the questions on the chat and save some for the next session, so you may continue.
Okay. Okay, so like uh, with regards to both like the standard planes that are taken by experts as well as the blind sweeps, like there are AI models that help in both of them. Like uh, there are models that do standard plane detection. So if you have multiple images that are standard planes, you could choose the better standard plane. With AI models, you could also like use segmentation models to segment head, abdomen, so you can automatically find important parameters such as head circumference or the femur length, these sort of things. And AI models can also directly estimate the gestational age. I showed you earlier that like AI models estimate gestational age better with blind sweeps than the gestational age estimated from fetal biometry taken by the experts. AI models also allow you to localize placenta, allow anomaly screening, uh, and these are sort of the AI models that are helping uh, radiologists to analyze ultrasound as well as helping to automate things. So now let's start with why preprocessing is necessary. Uh, the raw ultrasound that images that are acquired are actually like if you there are many devices. Some of them are handheld devices, some of them are costly devices, and like the images quality often vary among devices as well as device settings as well as the operator who takes them. So like the image content and quality is not consistent, and it is noisy as well, so it is often hard for AI to learn from them. And like without preprocessing, the model accuracy can be low. So like preprocessing makes everything like patterns clearer, and the data can be standardized. There are also some unique challenges associated with, particularly with ultrasound. The ultrasound images are like the beam mode ultrasound images are mostly grayscale, and they have like depending on the devices, they may have like low contrast, and there is often like grainy noise that occurs from the sound waves, like uh, entangling with each other, so it creates like Gaussian type of noise called speckle noise. So there are also shadows. Ultrasound waves are often blocked by bones, so like everything after the bones often appear as shadows. And you also require like gels to put before you use probes for taking ultrasound, because like if there is an air gap, then the entire frames will be black. So you have to take a bit care about like putting gel on, and like there should be no air gap between the probe and the skin when you take ultrasound. So but there are often like the cases where there are like dropouts, and the views aren't clear. And also like there are different machines, different settings, and different operators. Like this increases the diversity of the image. So these are sort of the unique challenges related to ultrasound. Like the preprocessing pipeline for dealing with this data often starts with collecting the data, and anonymizing the data, because like with DICOMs there are often associated patient information in the metadata, as well as like some of the times there are uh, patient related information directly engraved into the ultrasound images. So you have to take care about really anonymizing those kind of data sets. And you have to also like align the clinical measurements that are there. Like if you find if like a radiologist may take uh, the the head circumference measurement, and you have to like pair up the ultrasound data with the the clinical labels. And for data preprocessing, you could do image standardization, so that uh, like the ultrasound images that may come from different devices, so they may have different resolutions or different pixel spacing or like other properties. So you have to standardize all of those images into like the same standards, so that a model can like look all the images in a similar view. And another thing that you could do is like extract the region of interest. Like there are often many pixels that are black and that don't and many pixels that don't show any semantic content about the anatomy. So you could just crop those out and really give model what it needs. You could also perform other techniques to like reduce noise. We'll see some of them in the notebook that I'll later show you. So, and after uh, preprocessing, you may need to like standardize, as well as like find other the reason of interest, and like the same things that I talked to before. So let's look into things you would do before preprocessing. I already told you about the variables that need to be protected and not be stored up in the research data. This includes like patient names, medical record numbers, contact informations uh, that are often there on the metadata, as well as the imaging itself. Uh, so, like, here is one of the examples. You can see on the left the ultrasound scan, and you can see an anonymized data where you can see the name as well as the place where the data was taken. This is like the raw data you often obtain when you take ultrasound, and you have to convert, like, you have to mask these uh, terms, and so that like it is ready for research as well as for uh, for diagnosis. Here's an example on the right for the anonymized report. The name has been masked out. Like this is the way it should be when you take the examination and collect the data afterwards for research and other purposes. Uh, Another thing that you may have to care about in preprocessing for like the blind sweep data is to not use all the frames in the video, because like you could have around 200 frames for a single video. And like when you take a video, often the consecutive frames don't convey much additional information. So it may be beneficial to only use some of the keyframes rather than using all of them. And this could help the model not get confused over like the repeated information. Also, like removing lots of redundant data by sampling can help you to train the models uh, in computationally efficient manner, so you don't use a lot of compute to do model training. So when you work with videos, it is often important to do sampling or frame extraction. Then another thing is image standardization. Like before you feed the data to the model, you have to bring all the data into a consistent format, so that the model doesn't get confused from the diversity. like some of the steps that you can do is resize frames to a standard size such as 256 by 256. Mm, and you can do intensity normalization. You could like normalize everything with a standard mean and variance, so that like the uh, the distribution of the images don't get biased with uh, just the brightness or the contrast values. So if you normalize everything, it would come into a similar range. So like the features of the images wouldn't be biased to those factors such as brightness. And you could also do spatial standardization. You could like uh, bring all the images in the same location, maybe to the center of the image. Sometimes like when the images come out from the the devices in DICOM, some of the image, like the ultrasound fan, are way on the left. Sometimes it's on the center. So you could also do spatial standardization. You could also like increase the contrast if necessary, and you could resample to a standard dimensions. uh, like sometimes like some of the devices capture a different physical dimension than other devices, so resampling those into same dimension is necessary. We'll also talk about like resampling to a standard dimension later in the notebook with code examples, so you could see there as well. Like these are some of the steps that you include to standardize images. And another thing I talked to you earlier is the region of interest extraction. Like uh, you could crop the entire image so that only the fan of the ultrasound is visible, so the model can see more clearly the relevant information, like rather than giving it all the information that is there. And some of the times there are lots of texts in the imaging, so you could remove those texts. Like here is one of the example. You could see that after taking the ultrasound, the images come up with a lot of texts written there, including the the device settings that were present. So you could remove those sort of texts before you train it with your model. And there is also often this blob on the imaging. This shows like this shows that the that where the blob is present, this is the right of the patient. So you could also remove these blobs when you train the model wherever necessary. These are the kinds of things that you have to like think about when you pre-process the data. And there are lots of tools for pre-processing. You could use PyDICOM, as you will see, for handling with DICOM files. You could use OpenCV for image processing tasks, and you could use NumPy for numerical operations. You could use Matplotlib to do the visualization, and simple ITK for other image processing tasks. These are some of the tools that you can explore. And uh, yeah. And there are also things that you have to avoid, like uh, while pre-processing, you may like need to you should not like overprocess the data, so that like remove like overprocessing could remove clinically important features. For example, you could like uh, remove like small bright spots on the images, but by doing that you may sometimes accidentally lose relevant clinical subtle clinical features. So you have to be careful about not over pre-processing the data. And you could also like use the metadata information, such as for example the pixel spacing and uh, other like the frame rate. These kinds of information are often present on the metadata. So rather than only relying what is on the pixel data, you could also like see what you can do additionally with this kind of metadata that is present. And another thing that you may have to like be careful about is that different images may require different pre-processing steps uh, to come about in the like same standardization. So And another thing that you also have to be careful about is when you pre-process the image, you may also have to like do the same pre-processing steps to the ground truth annotations. uh, yeah, for example, if you have a sweep video and you do reversing of this video, then you may have to like think if the reversing changes your ground truth annotation, or like it gives you the same ground truth annotation. So these are the kind of things that you may have to be thinking when you do the processing of the data. And finally, when you have the data, uh, some of the data preprocessing done, you may then have to think about like uh, what are your constraints during the training, for example, on the memory side or on the compute side. So you may have to like resize the image to a particular dimension or use a particular model to fit your data uh, to accommodate like to do the training on the memory you have available. So these are the you may also have to think about like the memory management. We'll also have an example for data sets and data loaders later on the notebook, so you can also get hands-on with it. And another thing you could also do during pre-processing or like during model training would be data augmentation. uh, when you take like data from the ultrasound devices, like you have a fixed data size of the ultrasound images or videos, but then you have like unlimited settings. So in actuality, the variation in the data set itself or the variation in the real data could be very high. That is like often not captured with limited size of the data. So you could like do manual data augmentations to simulate some of those diversity that can actually happen on uh, real testing. So some of the things that you can do is like uh, maybe do small rotation uh, of the image to simulate the probe angles, or you could do flips of the images, or you could adjust the brightness or add some noise to like simulate the speckle noise that often occurs on the ultrasound images. So yes, like data augmentation can also help you to like increase generalization and robustness to the real uh, to when you test it in the real setting. This much from the slides. Next, I'll show you like a short notebook that I prepared so that you could also see how it works with the code. Do you have any questions with
Yes, we
this content?
yes, we do have quite a number of questions. You have received a lot of hand claps. I know you can't see them since our previous instructors couldn't see those, but then you've received so many claps and congratulations. So we do have a couple of questions. I'll just start from the very first one. I've been trying to answer some of them. So let me just do one question, you answer, and then we move on to the next. So, doesn't the model's ability to capture and analyze real-world photos get limited if we feed it processed data?
Sorry, get limited from.
So basically, when you feed the model with processed data, does it limit its ability to capture and analyze real-world photos?
Like uh,
So for yes, I can just explain a bit more. So for instance, currently we are collecting the standard ultrasound images and videos, the research videos, and you're going to be pre-processing this. You're going to be labeling so that you can train the model. So the question, this uh, I don't have the name yet. I copied them somewhere. The question that is being asked is when this model is finally accurate, 90 something percent accurate, 99% accurate, and you put it in the field, will the fact that you used pre-processed and processed data to train it limit its ability when now a nurse in a rural center goes to use the blind sweep and the model is automatically meant to? So basically, they're asking for you to explain whether it will have any implications.
uh, it might have, I think it might have some implications, but what you would do is whatever like the pre-processing that you did well when training the data, you would do like the similar set of pre-processing on when you like test it. So uh, with regards to like modal evaluation or like getting out the labels, you do the same sort of pre-processing with the assumption that it does not like sift your like it brings the same distribution as you did while training, but like when you do the real testing, there will definitely be some uh, distribution shift that can occur. So definitely the model accuracy might be lower than what when you validate and train the data, but yeah, there will definitely be some variations. So yeah,
All right.
you could also train the model actually to like to handle the distribution shifts, but regardless there will definitely be some performance degradation when you do it on the real world rural data. But I think yeah,
All right.
yes.
So thank you for that. Somebody had said you show the notebook, but then you're moving to that. So we'll pose that question. The next question was, who will decide which image should be used in pre-processing? So it was just a question, who decides which image should be used in pre-processing?
Like the the like you would see maybe from the data team or from the ML team, you see all the data that you have, and like you may also anticipate some of the data that can actually occur on the on the field testing. So you could like from the domain experts, with the help of domain experts, as well as like from the data team, do you would like guess or you would like research for the good kind of data preprocessing and like really test those to find the preprocessing. And does that answer the question, or like
Yeah, we'll hear from them. I think possibly I can also add that something that you're doing is a lot of quality checks so that whatever data is picked to train the model is already, what do you call it, is data that doesn't have to be sifted through, as you were saying. So with the quality checks that are being done in the field during data collection, then the data team won't have to really worry about trying to sift through it. But Mohammed will tell us. Next, we have a question. When cropping out text and artifacts, how do you make sure the model still sees enough of the fetal anatomy to learn correctly?
like when you sometimes like you may like when you have like consistent like you have text at consistent location, you could just like crop, or you could just like mask out those parts. Other times it is not like exactly uh, like perfect. You may have to sometimes like you can what you can do is like find a mask for the for find a mask for like some of the uh, ultrasound images, and train an additional AI model that like segments only the ultrasound fan, and you could like remove all the texts or things that are beyond it. So but it would also not be perfect because you are using an AI model, so it may be like it may not give like like good mask uh, for like when you have distribution shift on the images. So like you could try a lot of things. You could also like do other image processing tasks to like remove the text, but it may also not be perfect. So yeah, like the answer would be like you can try a lot of things, and but when you do real testing, it may not be perfect, but you could still like make the model robust with scale. So yeah.
All right, thank you for that. We've got two questions that are almost similar. What does ground truth annotation mean? And the other person said, please elaborate a bit on the ground truth annotations.
uh, the ground truth annotation would be like, for example, you if you have like uh, mm, like if you have like, let's start with blind sweeps. If you have like a blind sweep data, then sometimes like not sometimes, but like the radiologist also like take the standard scan of the patient. So during the standard scan they can find all the relevant information, uh, such as feature presentation that you can see on the middle of the slide, and they can also like find the location of placenta, or they could measure the like head circumference or find gestational age. So this would be uh, some of the ground truth data that can like occur alongside the blind sweep data. And sometimes like the experts take time to like find like the for example, for segmentation tasks, they do find segmentation of the head regions or something like that. And that would also be a ground truth data that you could use for segmentation tasks. Yeah. And yes, the ground truth just means that whatever variable you are interested to predict with your model, you would need those ground truths either from the experts or like from the annotations. This would be the ground truth data.
Right, thank you. The next question, how do you do augmentation and the codes? The question doesn't sound complete, um, but I'm seeing it's been updated. How do you do augmentation and the types of codes to apply to get at least 95% accuracy? I think that was the question. It hasn't been fully put.
Sorry, what do you
Yes.
do with augmentation to?
h- how do you do augmentation and the types of codes to apply to get at least 95% accuracy?
Like I wouldn't be sure about 95% accuracy. Like it would depend on what task you are interested in. Like when you do augmentation, for example, if you are interested to find like the feature presentation, then there would be augmentations that are like specific to imaging, that you can do for every tasks. And some of the augmentation will only apply for the tasks you're actually interested in. I'll also explain some of these in the notebook that I'll show you. So uh, you can be clever and define like many such augmentation scenarios that can actually happen in the real world. But I wouldn't be sure about getting 95% accuracy when you test it on the field. Uh, yes, and it will also depend on the tasks. And sometimes you might like really not need 95% accuracy as well, because what you are trying to do in rural settings is to see if you really need to go to the hospital or not. You might just be interested to screen whether this case should be referred to the hospital or it's fine. So uh, like if you could get the referral right, then it might be enough in those cases as well. So yeah.
Yeah. And there's a question on which data is better for pre-processing. Although I'm saying it's been answered, but then I'll still ask it because part of the answer has a couple of more questions. Is it video clips or still images? Although considering video clips are picked by the probe, still images are picked by the main ultrasound machine. Maybe you'll answer that. And in the same the same answer, maybe you can talk about the frames, the frames within the videos. Who decides which frame should be used in the pre-processing?
Mm, like to decide which like the actually the like would like to find the right sort of frames in the video also like could depend on the tasks. So for example, when you do like the age estimation for the child, you might like you might also like shuffle the data because you might not be the temporal information in the video might not at all be relevant. And like when you do like the feature presentation identification, then the temporal information such as when the head appears is important. So like in those cases you would uh, you would want to like you would want the video to have the entire frames so that so that the model can use the temporal information. But when you do like the gestational age estimation, you might just like remove most of the frames and like try to find the standard frames, like the standard frames that often carry the information related to like the size of the fetus that is related to the age. So like the the frames to pre-process on, like normally you would apply the pre-processing to all the frames in a video. You could also like do selective, you could also do something like selectively applying pre-processing to some of the frames to test whether the model like performs good on the test set. But like you could try a lot of things in this scenario, but uh, yeah, it would depend on the tasks that you'd do on the downstream. So yeah, I think that is the answer for the second question. What was the first?
Yeah,
Uh,
yes, the first was this, which data is better for pre-processing, video clips or still images?
I think like both of the things should be pre-processed when you do model training, uh, because yeah, because like both of like for the videos as well as for the images, you would want to standardize them before you do medical training or model training. So it would like it is necessary, or like it would be better to do pre-processing to both of the for the still images as well as the videos.
All right, thank you. So I'll just ask the last question and then all other questions we'll ask after you've done the notebook. This last one is similar to what you've been speaking about. And basically, somebody was saying they've had a chance to use AI for pregnancy dating. However, the model seemed to have been trained on images with poor resolution. While during their usage, they used a high resolution machine and found the model performed less accurately by 4 to 5 days. But when settings changed back to poor resolution, it was excellent. So their question is, how can AI image processing balance and enhance the model even when exposed to two different image resolutions, but same image features?
Okay. uh, like image you could also sometimes you could like there is a variable called like the pixel spacing that often captures different physical dimension on like different physical dimensions regarding the image. So you could like in those cases you could convert the pixel spacing to like to a common spacing so that it represents like so that the like the distance between two pixels always represents the same dimension or like the same spacing between in the physical space. uh, Maybe if that's the case, then it is like good to bring all of the data in the same physical dimension. And regarding like the resolution, like we'd have to try a lot of things on it. So uh, definitely the reason for like having bad performance on like a different resolution is uh, because it has not seen those data in the training side. So maybe like if you could include the images of higher resolution also on the training, then it would definitely, I think, would increase the performance while you test. But if you don't have like the resolution of like if you only have like high resolution on the testing side, then maybe you could like manually reduce the resolution of the images that you have for testing, so that you test on the similar distribution as you have on the training. But yeah, you could try that on during the testing. You could just like, for example, reduce the resolution for testing, so it might work. Or like it could still have some uh, distribution shifts. So yeah, you could try those things.
Right, thank you. So we'll hold all other questions until the end of your next session. So you may continue with the next session. I'll keep track of the questions. I know we have one from Saroj. We'll answer that one after.
Okay. Mm, can you see the notebook?
Yes, we can.
Okay, like uh, I wanted to like give like basic like some of the like you could how you could do pre-processing on with the codes. Like I wanted to explain like how to work with DICOM data, and like some of the pre-processing things that you'd do in actual settings. So let's begin. So like most of the times when you have ultrasound data, it's with the DICOM format, because the DICOM format captures both the metadata as well as the pixel information. It also defines the communication protocol. So like it really makes it easy for different devices to share the same format. uh, DICOM organizes the data in a hierarchy. For example, a patient might have multiple studies that are done on, like, for example, on different follow-ups, and each study might have like multiple uh, acquisition of sweeps or scans, and you also have an identifier for each of the DICOM file, and these are actually captured in the metadata. And yeah, you have like the ultrasound, okay, sorry, the DICOM file stored the metadata information in like dictionary likes with group and element. Group defines a particular set of tags. For example, like a group code might define all the information related to a patient, and the element would be something like patient ID, patient name, or contact information, like everything related to patient. So, and it also defines a transfer syntax. So it can have like you could store an uncompressed image, or like compress the data for like efficient storage. You could do those kinds of things with DICOM. So there's a library called PyDICOM. You could use PyDICOM to like work with DICOM images. Like what I've done here is taken a simple uh, uh, a, 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 a sweep video of a patient, and like this is like you use DCM read method from the DICOM library to read the image. And yeah, you could access the names of the attribute in the DICOM. For example, the patient name, you could see the patient name here from the just from the attribute of the object of the data. So you could like print out the patient name as well as the instance UID. This means the ID that is given uniquely to each DICOM, and you could also see the series UID, that like if you have multiple DICOM files, or you have multiple series in a same visit, you could have like multiple identifiers to identify those. uh, yes, and the patient name here has been anonymized. like uh, like the patient names can also appear here. And before I was talking about the necessity of anonymization in the presentation. So you have to anonymize this sort of personal information uh, when you like use DICOM for research and all. Here you can see like the study ID. You have this was the like study taken at a particular date. So you have the study ID. There is like one series of like 8 sweeps. So it's you have a series information here, and like the IDs of multiple DICOM files, namely the 8 sweeps that are taken under this. These are like some of the things about DICOMs and the structure with which DICOM stores the data. Uh, and you can also have like with DICOMs the information specific to ultrasound, such as modality, which could specify that it is an ultrasound. So you can also have like the number of frames, frame time, and other information such as pixel spacing. The pixel spacing defines like like the distance in the physical space that any two consecutive uh, pixels represent. You can also capture that information in physical delta x. It also like captures what is the physical uh, what is the physical dimension that two consecutive pixels take in the actual space. And like the attributes such as physical unit would give the unit that is like that will basically provide the unit for the pixel spacing. And you could also have like other things such as uh, acquisition parameters and other device settings. You could also like get the
Nisant, we lost you. All right, let's just wait for Nisant to come back. I think maybe something happened to his internet. I thought I was the one who lost my internet, so let's just give him a few um, minutes for him to be back. Just let's give him a couple of minutes. They ended up having a power outage. So that normally affects the internet, affects um, anything else that uses power. So let me see. All right, so it's back. So let's give him a few more, like a minute or so, he will be joining back. I'll still keep picking your questions. Kindly type out your questions. I'll keep track of them so that we don't miss any. Yes, Peter, Global South problems. All right,
Hi,
welcome back.
Victoria.
Hi, we were
Oh
just
yeah,
saying these are Global South problems. We all know how it goes.
yeah.
Yep.
Share my screen again. Okay. Can you see the screen?
We can.
Okay. Yeah, and to continue, like you would have uh, some of the uh, like the tags to define like in which representation the pixels are specified, or and also the bits allocated for them, whether the representations are signed, unsigned. You could see like you could just get those with from like the attributes of the object to find those sort of things that could be relevant to you when you like pre-process the data, or could be relevant for like other tasks. Yeah. And like I want to show you the how pixel spacing works with ultrasound. Like okay, here is an image. Firstly, uh, the image has a pixel spacing of 0.39 comma 0.39. This means that each pixel here, like each consecutive pixel represents 0.39 millimeters in the x direction as well as in the y direction in the real physical space. So like the image, if you like multiply 500 with 0.39, you would get the the physical height that the image captures. And like it's often the case that when you take uh, like ultrasound images from multiple devices, you have pixel spacing that is different from each other. Sometimes like when you take with a same device as well, you have different settings, so like the pixel spacing is different. So you can actually resample the pixels to have a consistent to have a consistent like spacing in the physical space. For example, I've like decreased the pixel spacing here from the original image. You would get like some, if you decrease it, you'd get something like a bit zoomed in. And if you like increase the pixel spacing, then the images would appear a bit smaller here. So like if you have like pixel spacing with spacing from multiple that is different, then you could like standardize this as well to a to a like a common spacing to yes, to standardize them. And here you could go through the code. I'll like share this notebook to how to do this. Regarding like text and indicator blobs, you could like previously I showed, you could just manually crop them to get like the image that is text free. Or you could do something like opening operations, like morphological operations to like close all the bright, like small bright spots. Like here I've used this technique to remove the text. It's not perfect, and the image is a bit different, but it might be like appropriate to try whether like applying this operation to remove the text would give better performance in your downstream task. So like this 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 kind of things can be done. And another thing is like enhancing the image that you already have. For example, you could do like median filtering or bilateral filtering, and you could also do some operations in frequency domain, as well as you could do like wavelet based enhancement. For example, I've shown here a median filtered image from the original. It just takes like a patch and then finds the median within it, and and like replaces the every value from with the median of the pixel intensities. And like you can see that there is a bit like sharp sharp irregularities here, and those kind of things are a bit blurred out here. You could do that, or like you can also convert the original image to frequency domain, and you can like uh, you can only use the low frequency components to reconstruct a low pass image. Or you could like uh, or you could also like filter the texts using high pass filters. So you can find like the high frequency information can be filtered out using like only the high frequency components from in the frequency domain. And another thing is like wavelet based decomposition. Like what you can do with wavelets is you could like do you could separate the low frequency as well as high frequency components in like multiple scales. For example, if you apply a wavelet best transform to an original image, you can get like four different images of lower resolution. And like each of the like one of the image captures all the low frequency components, and the other images capture the high frequency details that are there. You can like do image resizing using wavelet based transform. So like the resizing occurs, like you don't resize in a normal like way of like leaving out pixels. You can do like more clever such as wavelet based transform to do this. And you can also like do wavelet based transform for the only the low frequency component to get like more multiple resolutions of this image. Yes, these are the kind of things you can do. And you can also use like deep learning based enhancement techniques. You could use GANs or units that denoises specifically for the speckle noise and other kinds of details that are there on the image. And like also regarding augmentation, you could do like intensity based augmentation, such as brightness adjustment, contrasts, like introducing noise to enhance, like to get the variability in your data. And you could also do like random masking. Like random maskings can help you simulate things such as when you have contact loss with the probe, or like when you have a shadow with bones. You could like this random masking can simulate those kind of artifacts that occurs in the images. And you can also do like non-intensity based augmentations, such as uh, like spatial augmentations like horizontal flip, rotations, and cropping, zooming. And you for videos you could do temporal augmentations such as sequence reversals and frame rate variations. You could like speed up or slow down the videos. These are the things that you can do. Like you don't have to do everything for any particular tasks, but like you can try multiple of these or a combination of these techniques to do augmentations. I have some of the examples of augmentation, such as like increasing the brightness or contrast, or like doing gamma modifications that like sharpens the bright part, like that sharpens the dim part but does not affect bright part as much. Like these are some of the clever transformations that you can do. You could add Gaussian noise to simulate the real world setting, or you could do like blurring. Like with videos you often like have blurred effects because uh, you have a motion, and when you have motion you can have like motion blurs, and like those kind of things can also be simulated with augmentations. And you could also do random masking. I think it's the random masking is missing here, but yes, you could also do that. These are some of the like these were some of the intensity based augmentations. Like with intensity based augmentation you could like do it to like for every tasks. uh, but for like semantic based augmentation, it could change the semantic information of the content, so you might have to be careful when you do like semantic based augmentation. For example, if you do horizontal flip, then you have to be careful that the horizontal flip would actually make the right side of the patient to appear on the left. So like if your task really needs to find the left position of the patient, then this might be a bit like this might not be the best thing to do. You could also like rotate the image or scale it. With videos you could like reverse the sequence of the video, or like speed up or slow down just to increase like the variability. Because like when an operator takes sweep, then like in some part he or she may like speed up, or and in other parts he may slow down. So you can simulate even this with better sampling and with augmentations. So these things might be helpful. The key things that you have to think for augmentation is like you have to be like aware of the task that you are going to do. So like semantic augmentations can distort your labels if you apply it blindly, so you have to be careful on that side. And like you could do intensity based augmentations to multiple tasks to just like to handle robustness to multiple devices. And regarding like when you do augmentation, you have to like you like the augmentation should actually make sense, in the sense that it would actually occur in the real world setting. So you have to always ask, would a sonographer realistically see this transformation in practice? So, and also like too much augmentation can like produce unrealistic examples. I've also created a pre-processing pipeline on HC18 dataset. This dataset contains ultrasound, like 2D ultrasound images of a particular standard plane, that is of the head of the fetus or the baby. So with in this task you have to like find the head circumference based on the image. uh, I have like written all the codes here. You can download the data. And like first thing you do with after you have your dataset, you download the dataset, is defined with PyTorch. You defined dataset class. And with dataset class, you what you do is just you load up the, like you can provide the file path to your images or videos, and like you can write the code to load up the the images. And like you can apply whatever pre-processing that you want to apply with the transforms. And the I've defined the transforms here. Like for the for this particular data set, I've resized the image to 224 by 224. I've like for the grayscale I have outputted 3 channels. I've done horizontal flip, uh, done some random rotation, converted the thing to tensor, and normalized with this particular value. So why choose this particular value? Because for normalizing, it just means you subtract like every pixel value in every channel with these means and divide by the standard deviation to normalize. With like I've choose this particular value because uh, later I use a pre-trained image, a pre-trained model that was pre-trained with ImageNet data, and ImageNet data actually uses this normalization. So the model is adapted to see the pixel range with this normalization. So I've done the same normalization. So you also have to be careful when you use a pretend model. Then you may need to like re-normalize or normalize your data set to like to the same standards that the model was previously trained on. And also like when you do augmentations such as uh, random horizontal flip or random rotation, you only do this for the training, because uh, with the validation you want to like access, or sorry, you want to assess the the validation that does not on the same validation set every time. So you don't want to change your validation set. So you and you want the validation set to be the actual real world data or something like that. So you don't actually augment the data in your validation set, but you do like perform every other normalization similar to the training data set. And an augmentation can also be done offline or online. Offline method means that you do augmentation before you create the data set class. So you keep all your augmented data set. You do augmentation and store all your augmented images or videos, and you load up the 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 entire collection that you do after augmentation. You could do that, or you could also do online augmentation. This would be like storage efficient. With online augmentation, you augment the data as they come on while you do the training. So like you can do these like both of these, but like offline would make things like you would require a bit more storage depending on how much augmentation you do. Then what I do is I like load up the data set uh, and split the data set into train, test, and validation. I like to just to recap. I defined a dataset class that would like load the data from the files, and I also defined the transformations to apply. This would be like the image pre-processing, and these transformations would apply the transforms to the loaded images or videos. And then like then I and what I do then next is split off the dataset into train, validation, and test. And then after that I define a data loader. What a data loader does is you like give it the dataset class that you defined earlier, and the data loader like would uh, get other parameters such as batch size, whether to do shuffling or not, and how many like CPU workers to use on pre-processing. Like this, you can give these kinds of parameters to the data loader, and the loader automatically like creates the data of a particular batch size that was particular batch size, and handles everything else. And then I uh, get a simple ResNet model and put a linear classifier to like train for train the model. And yes, like what I do here is okay, just to give you the visualization, I can go here. The data set that we have here is like this sort of images, and our goal was to find the head you have the head here, and the goal is to find the head circumference automatically. And yeah, I was showing you for this setup. So like we do the training, and yeah, we get the results. You can look at the notebook later on. I'll be saving this notebook once I like I'll check everything once again, and I'll share you the notebook, so you can also get hands on with it. I think this much, I prepared this much in my notebook. I'm open for questions now.
Thank you so much, Nisant. I believe everybody can say that was an amazing session. Um, and you will be getting access to I'm hoping you can see the claps. You will be getting access to the notebook. So I'll go through the questions. I've been trying to keep track of them. I'm hoping there's nothing I've missed so far. So the first question is, what are ultrasound models usually trained to do? Just in like some ideas of what ultrasound models are usually trained to do.
Like like there are like countless of things that you do with ultrasound models. Uh, like from what I showed you, you could do screening with like gestational, like finding gestational age to monitor the uh, the growth of the fetus. You could like detect many complications such as the placenta appearing on the cervix of the mother. These are the like some of the things that you do to monitor the fetus. So you can do the ultrasound model training for these kinds of tasks. You to directly like find whether there is an anomaly or to estimate the age. And another set of tasks would be like to help the radiologists. Maybe like some of the there are some of the models that like they score the standard planes for like for the images. So like it's helpful for experts to find, like they can go, or like they could take the sweep and they can easily find like, oh yeah, this is the like right plane from and yes, some of the ultrasound models do that. And like there are ultrasound models that like also help experts with the guidance itself. So for example, uh, the model would like provide it the directions to go here, there, to find here and there, to find like the right sort of views quickly. So like you could yes, and like AI also helps do these kinds of things. And there are AI models that also do segmentations. Like with segmentation you could like find the region of interest automatically, and if you're interested in measuring or taking the biometries, you could like automatically do that. So like there are countless of applications that ultrasound models are being used. And yeah, I hope that answers the question.
I think that sufficiently answers that question. All right, the next question was, which patient in the data set has multiple sweeps, and each sweep contains multiple images? When feeding this data into the model, should the input be organized so that the model knows which images belong to the same patient and the same sweep, or can the images be treated as random independent samples?
uh, uh Normally you'd like you when you do like model training, you want to find like you have, for example, you have a patient, and each patient can have multiple sweeps, and each sweep can have multiple frames. But when you do like tasks such as gestational age, for example, finding gestational age, you'd you'd want to find the right age for a particular patient. So like you'd want to infer for a particular patient using all the data you have, meaning all the sweeps and all the frames in each sweeps. But like using, because the blind sweep, for example, with eight sweeps, you have eight like 8 videos, and with each video you can have like 200 sweeps, sorry, 200 frames. So it would be a lot of information for only one patient. So like you definitely need to like group the videos or the frames for each patient, but you could but like it's like you don't have to use everything for diagnosing, because like using because there is a lot of redundant information there in the entire sweep sequence and the frames. So you can like selectively do, or you can like randomly sample some of the frames, or like few videos depending on the tasks. So yeah, that's how it normally works.
All right. Oh, okay. There you go. Thank you. The next question is, and I think he already answered this, so I don't think you have to answer that. Whether it's okay to share the link for the Google Colab for your notebook. I think you already said yes, we'll be sharing, and we will be putting this as a link within the learning management system, so you'll all be able to get that. So the next question is, why is the number of channels 3 in the ultrasound image? Shouldn't it be just one?
Mm, uh, you could you could like use only one channel, uh, because like uh, for all the 3 channels it's you will only have redundant information. But uh, you could write a model, or you could use a pretend model for that works on a single channel. But like here I used the model that was trained on ImageNet. So because like ImageNet is trained on natural images, and sorry, the model was pre-trained on ImageNet. And like because the natural images have like 3 channels, and do I wanted to like have 3 channel image for that as well. So that's why, just to be like standard or consistent with what natural images already have, like I use 3 channels. But like you could only use one channel, it might be more like efficient computationally to use only like grayscale channel. Yeah, but particularly I did that for because of the ImageNet uh, channels.
All right, thank you. We have so many other questions. Let me just keep asking them. Would it be beneficial to fine-tune models for each individual user to adapt to their scanning style and gain personalized insights, or would the resource requirements outweigh the performance gains?
Mm, you could definitely try that, like to get to tune on like if you have such a huge amount of data for each patient. You could try that for single patient. Or what you can also do is like uh, in a single setting, for example in a single district in Nepal, or in a single like region in any country, you could like fine tune or do adaptation on like the local data, so that it so that you can handle the distribution shift from the originally pre-trained model to like the localized context. So you could do like personalized fine tuning, as well as like fine tuning for a particular device, because there is lots of variability in devices. Or you could do like fine tuning for a particular reason, so that you can adapt it. Like you can do multiple things. uh, I wouldn't be sure about the performance, because like you have to do it to know. So yeah, there's a lot of room for exploring here.
All right, thank you. I think we have like only 4 more questions. Can blurring be used for noise reduction during image processing, like Gaussian blurring, average blurring, median blurring, or bilateral blurring? And among these techniques of blurring, which one is more safer for ultrasound images?
Mm, yes, you can definitely use blurring, because like with blurring you could remove some of the like high frequency noise, or like the spike in intensities that can occur natural that can like occur in ultrasound images. uh, I think like bilateral blurring is good, as well as the Gaussian blurring. But like you have to try you could try everything, uh, but it's normally the case that more advanced technique perform a bit better, but it also means a bit to lose on the compute side. So like sometimes when you use a more complicated algorithm, it might make more like it might be a bit more compute heavy, but the performance gain is very minimal. So yeah, I'm not sure about like which algorithm to use particularly, but these are the trade-offs that you might have to think when you do uh, like when you use blurring to do the processing part.
All right. Thank you for that. This is just a comment. Looking at the amount of work and size of data of the images, this does not seem to need usual laptops or computers. This is mega size and data. So I'm thinking the person is just saying you can't use a normal computer on this. Maybe just clarify that and then go to the next question.
Yeah. That's definitely spot on because we're also having lots of trouble to like to reduce the redundancies and to like find the right sort of views to like efficiently work on the compute we have. It's definitely not possible when you have to look into multiple frames and multiple videos with only your laptop. Yeah, but you can definitely use some clever techniques to reduce the compute uses. uh, but like you're spot on that that it's very computationally challenging. Yeah, we also like one of the like I think the most like the major problem we have when we are working with the blind sweep data is how to uh, do things efficiently with the models we train. So yeah, that's a bit challenging.
Right, yeah, I do agree. I've been running a reduction code, something so simple just to redact our images. And I'm not running this online. I'm doing it directly on my computer. And when it's running, I normally have to give myself some some time off. But yes, the compute is high. The next question, to come up with this model, what main features do you focus on to bring out what you require of the model to come up with?
Basically it also like everything else, it also depends on the task. Like some of the tasks might require uh, like the information from the fetus, such as the head or the abdomen or like the overall anatomy of the fetus. Sometimes it's also necessary to like to see the maternal anatomies, like the cervix, to find the for example the placenta location. And like sometimes like both the fetus as well as the maternal anatomy is important to like assess, for example, when we do quality assessment with automatic quality assessment with blind sweeps. You have to like the model looks both at maternal as well as the fetal anatomy to like to assess the quality. So it might depend on the tasks that you are looking into, but like but when you but it's like it is obvious that you have to always look at the fan of the ultrasound. So
All right, I'm not sure what happened. Um, I think we lost Nisant again. We only had two more questions. Let me just find out.